Welcome back everyone. In this lecture, we will actually study the automorphism of groups. So, we have already actually defined these automorphisms of given groups, okay, and then the set of all automorphisms with respect to compositions, they themselves form a group. So, we want to understand some of its properties. Okay, so let's recall some of the notations that we have already used. Okay, we denote G by a group. So with respect to some binary operation. So now what is an automorphism? So any isomorphism of G, okay, that is called automorphism. Okay, so let me write down very explicitly what it is. So a map tau from G to G, okay, is called an automorphism of G. Okay, so this is the definition. So if tau is an isomorphism. So what is the meaning of that? So first of all, tau is a bijective map, and the second thing is tau is actually a group homomorphism. Whenever you take xy from G, then tau of xy should be tau of x times tau of y for all xy in G. Okay. So this is the definition of automorphism of G. So now what one can do? One can collect all possible automorphisms. Okay, you collect this automorphism of G. So which is a subset of this SG. SG is the set of all permutations or set of all bijective maps from G to G. Okay, so automorphism of G, they are special bijective maps. So they also kind of preserves the group structure. Okay, they are bijective maps that also preserve the group structure. So now if you take the set of all automorphisms, the set of all automorphisms of G, then this automorphism of G is a subgroup of SG. So SG is a group with respect to the composition of maps. Now it's clear that automorphism of G is a subgroup of this SG. So now we also have very special subgroup of this automorphism of G, which are called inner automorphisms. Okay, how one can define this? So for given any element G in G, so one can define a map called tau G from G to G. So that is just given by what is called conjugation. So you take this x goes to this G x G inverse. So for all x in G, so this is the map. Then one can verify that this tau G is indeed an automorphism of G. Okay, this is something we have already verified. I will actually leave it to you to verify again. So this is an automorphism of G. So in particularly what we have done, we have defined this map. Okay, let's call it tau again. So which is a map from G to automorphism of G. So which is given by small g goes to tau G. Okay, so maybe I will use some other notation just to distinguish this from the earlier maps. So maybe I will call it pi. So let's call it pi and then you send it to pi G. So what is this pi G? So this pi G is this given by this inner automorphism, x goes to gx G inverse. Okay, so now you can see that this pi is indeed group homomorphism from G to automorphism of G. Okay, so here is the claim. This pi is the group homomorphism. Okay, so why is that the case? So let's look at pi of some G G dash. So this is going to be exactly pi G G dash. Okay, so which is a map from G to G dash, sorry, G to G. So what this map does, let's check. Pi of G G dash, when you apply it on x, then you get G G dash x G G dash inverse. So this is conjugation by this product G G dash. So then you can see that, So this can be rewritten as follows. So this is G dash X G dash inverse, and then you take again conjugation by G. Okay. So that means this can be obtained as follows. You first apply pi G dash on X, then you apply pi G on this pi G dash of X. Okay. So that tells you that this pi G dash of X is nothing but pi G dash composition, pi G composition pi G dash of X, and this is true for all X in G. So that means when you think it as a map, then pi G dash is same as pi G composition pi G dash. So that is same as saying pi of G dash is same as pi of G times pi of G dash, and this is true for all G dash. Okay. So that means this pi is indeed a group homomorphism. Okay. So once it is a group homomorphism, let us look at the kernel of this map. The kernel of pi, what it is? This is going to be those G in G such that pi G has to be a identity map on G. So this identity map is defined from G to G such that identity G of X equal to X for all X in G. So now if you think about it, when this pi G becomes this identity map, so let us spell it out and then see what happens. So pi G of X is going to be G X G inverse. If it is equal to identity G of X, which is X, then that says that if and only if G X G inverse should be equal to X for all X in G. Okay, this should happen for all X in G. So that means what? That means, so this is if and only if G X equal to X G for all X in G. So that means if and only if this G should lie inside your center of the group. Okay. So that means the kernel of this pi is exactly the center of your group. Okay. So you have the map pi which is defined from G to automorphism of G, where G goes to this pi G, and then the pi G is a map from G to G given by X goes to Gx G inverse for X in G. Okay. If you take this particular map, then the kernel of this pi is nothing but the center. So that means the G modulo the center using the first isomorphism theorem is isomorphic to the image. Okay. So if you think about it, this image is nothing but all possible inner automorphisms pi G, where G comes from G. So this deserves a special notation. So this is defined to be inner automorphism of G. Okay. So from this you can easily see that G modulo center of G is isomorphic to this inner automorphism of G. So this is called inner automorphisms of G. Okay. Not only that, from this you can see that this is a subgroup of automorphism of G. Okay. So that is obvious. But more than that happens. So if you take this inner automorphism of G, it is not only just a subgroup, it is indeed normal subgroup inside G. Okay. So how one can see this? So let us look at normal subgroup in automorphism of G. So let us take some automorphism, call it let us say tau, which is from automorphism of G, and then take some pi G from this inner automorphism of G. So then what I want to do? I want to compose tau pi G tau inverse, which is a map from G to G, and then look at what it does. So let us compute it on some particular element and then see what it does. So you take tau pi G tau inverse of X, then you get exactly equal to tau applied on pi g applied on tau inverse x. Okay. So, then you can see that this is exactly equal to tau applied on g tau inverse x g inverse. Okay. So, now tau is being a homomorphism, you can see that this is going to be exactly tau g tau of tau inverse x tau of g inverse. So, but tau of g inverse is going to be tau g inverse. So, this is going to be exactly tau pi g tau inverse of x is exactly equal to tau g x tau g inverse. So, which is nothing but pi tau g of x. So, basically if you take tau pi g tau inverse, it is nothing but conjugating x by tau g. Okay. So, that means, and this is true for all x in g. So, that proves that tau pi g tau inverse is exactly same as pi tau g. Okay. But which is an element of inner automorphisms of g. Okay. So, this proves that the inner automorphism of g is a normal subgroup inside automorphism of g. So, in particularly once you have this normal subgroup, then we can talk about the quotient. So, then you look at this automorphism of g modulo this inner automorphism of g, and then you take any particular coset and then look at the coset representative, and that will be called outer automorphism of g. Okay, or any set of representatives from this quotient, okay, automorphism of g modulo this inner automorphism, they are called outer automorphism of g. Okay. So, here we have verified that this set of inner automorphism that will form a normal subgroup inside this automorphism of g, and not only that, this g modulo the center of g naturally isomorphic to the set of inner automorphism of g, which is a normal subgroup of automorphism of g. Okay. So, this way we have so many interesting identifications. So, now this is something if you think about it, this defining this conjugation. Okay. As long as you have a normal subgroup, this is still one can define. Okay. So, what I mean by that, okay, this situation that I have explained earlier using the group, so that can be duplicated using the normal subgroup. You fix a normal subgroup inside G, okay, then we know that G H G inverse is going to be H for all G in G. So, that means we can make G to act on this H via this conjugation. Okay. So, G naturally acts on H via conjugation. So, what is the meaning of that? So, you can define this map pi H, which is from G to now automorphism of H. So, given by you takes any small g and then map it to this pi, okay, maybe I will put this H on the top. So, pi H G, which is a map from H to H, where it takes x to G x G inverse. Note that for any x in H, okay, this G H G inverse is going to be in H, and it is obviously bijective map and it is a group homomorphism. So, this is indeed a map from G to automorphism of H, and as before one can check that this map is indeed a group homomorphism. I will leave it to you to check, and then you can actually work out what will be the kernel. The kernel of this pi H is going to be those G in G such that this pi H G should be identity on H. So, then if you just work it out, so this is going to be exactly all the conjugation G x G inverse should be exactly x for all x in H. So, that is nothing but the centralizer of H in G. Okay. So, I will leave it to verify these two facts. So, verify that so you indeed get this group homomorphism and the kernel is indeed given by the centralizer of H inside G. So, now you can see that using this map, then G modulo this centralizer of H is embedded inside automorphism of H. Now, one can replace G by the normalizer, there is no issue. So, as a corollary, you replace G by the normalizer of H, then you can see that the normalizer of H modulo the centralizer of H is naturally embedded inside automorphism of H, because the normalizer is going to be invariant under the H is going to be normal inside the normalizer. So, note that H is going to be normal inside the normalizer of H. So, then because of that, so this corollary is true for any subgroup H in G. So, we can have this normalizer of H modulo Cg of H is sitting inside automorphism of H. So, why such observation is important? Sometimes we may have more information about this quotient, this normalizer modulo the centralizer. So, that tells you that such a group sits inside this automorphism of H. So, that means this automorphism of H must be somewhat large, it is not something very small. Okay, so this is somewhat very important observation. So, at least for theoretical purposes. Okay, so now what we are going to do, so I am going to just apply these observations to prove some very cute results. Okay, so for example, one can prove that. So this is a fact. So I guess I have already stated this. If you assume that G modulo the center of G is cyclic, so then G must be abelian. So there are many proofs available in the literature. For example, you can work with this G modulo center of G, which is a quotient group. Okay, so then if you take G modulo center of G, if it is cyclic, then you can say that this will be cyclically generated by one particular coset, which will look like G ZG. Okay, so in particularly all the elements here will look like G power k ZG, where k runs over integers. So, using this information you can directly verify if you take two elements from G. So, because modulo the center of G, this is cyclic. So, from that you can say that the commutator of that should be identical. Okay. So, but what we are going to do now, we are going to use this information G modulo the center of G is indeed isomorphic to this inner automorphism of G. So, once we know that this inner automorphism of G is cyclic, then we directly prove that G must be abelian. So, let us see how one can prove this. So, we know that inner automorphism of G is nothing but given by all this pi G, which are all conjugation maps where G comes from G. Now, since it is cyclic, okay, once you assume this is cyclic, so then that would imply that the inner automorphism of G is nothing but generated by, let us say, some pi x power k, where k runs over integers. So, note that pi x square is going to be given by, okay, when you apply it on z, it is going to be x square z x power minus 2. So, this is exactly x z x inverse x inverse. So, you apply pi x twice and then apply it on each. So, pi x square is same as pi x square. Okay. Now, this computation you can do it for any powers. So, pi x power k is exactly equal to pi x power k. Okay. So, this is something you can verify. So, once you know this, then what happens? So, you start with two elements, let us say A B from your G, then look at the commutator A B. The commutator AB is given by AB A inverse B inverse. Okay. So, we want to say that G is abelian, that means this commutator is identity. So, how do you say this? Okay, first look at this commutator. So, you can write this in the following form. Okay, this B A inverse B inverse, this you can group them together. So, if you group them together, this is going to be what? This is A pi B of A inverse. So, that is what it is going to be. But pi B is coming from this inner automorphism of G. So, this is where this pi B is coming from. So, then pi B can be written as pi x power k for some k in integers. Okay. So, that means you can write this commutator AB equal to A times pi x power k A inverse. Okay. So, that is what? That is A x power k A inverse x power minus k. So, this is how you are writing. So, now if you think about it, okay, so when you take this x and then if you commute with this A, let us see what it is giving. Okay. So, if you prove that the x and A commute, then from this you can see that this commutator A x power k will be identity. Okay. So, this is going to be the commutator A x power k. If A and x commutes, then A x power k will commute. Okay, that is obvious. So, that is what we are going to compute. Let us compute x A. So, x A is going to be x A x inverse A inverse, but note that this A x inverse A inverse is again given by pi A x inverse. Now, pi A again can be written as some pi x power r. So, if you rewrite that, this is x power r x inverse x power minus r, but everything is in the power of x. So, that means they all get cancelled, you get identity. So, that means x A commute. Since x A commute, that will imply that x power k A commutes. So, that means this A B that we have started with commute, because that is what it is here. Okay. So, this is one way to prove that using the information about inner automorphism of G, that your group G is abelian. Of course, the telling anything about the inner automorphism of G is same as saying that telling the group modulo the center. Okay. So, now I will leave it as exercise. For example, from this you can easily conclude that if the cardinality of G modulo center of G is less than or equal to 3, then G must be abelian. Why? Because if it is cardinality 1, 2 or 3, then the G modulo center of G as a group, it must be cyclic group, and you can see that once it is cyclic group, then this must be abelian. Okay. So, that is what it is. So, now let me just give one or two example of explicit computation of this automorphism of G. Okay. For example, first what one can do, one can actually look at this Klein 4 group. Okay. The Klein 4 group looks like Z modulo 2Z cross Z modulo 2Z. So, this is the Klein 4 group V4. Then if you take the automorphism of this V4, so you can actually use some linear algebra to compute this. Okay. So, note that if you take any x in this V4, 2 times x is going to be 0. So, that means this V4 can be viewed as Z modulo 2Z vector space. Okay. So, this Z modulo 2Z is a field. So, in particularly this V4 can be viewed as Z modulo 2Z vector space. So, then the cardinality of V4 has to be just the power of the dimension. Okay. So, Z modulo 2Z power the dimension of the V4. So, you can see that which is exactly 4. So, the cardinality is 4, the dimension is 2. Okay. So, in particularly once you have identified this, then V4 is a 2-dimensional vector space over Z modulo 2Z. So, that is how we are viewing. So, now it is not hard to see that any group automorphism of V4 is nothing but Z modulo 2Z vector space isomorphism. Okay. So, this is something I will leave it to you to check. So, here is the exercise. Any automorphism of V4 is a Z modulo 2Z vector space isomorphism, and conversely and vice versa. Okay. So, converse is also true. So, any Z modulo 2Z vector space isomorphism must be automorphism of V4. Now, using this observation you can see that, so the automorphism of Z modulo 2Z cross Z modulo 2Z is going to be exactly equal to GL2 of Z modulo 2Z. Okay. So, this argument can be generalized for any P group. Okay. For example, if you take Z modulo PZ cross Z modulo PZ, if you take this abelian group, so then the automorphism of this is again from the earlier argument going to be exactly GL2 of Z modulo PZ. So, if you are not comfortable, you can put isomorphism here, not a problem. Okay. So, this is one way to do it. Again, if you think about it, if you take any Z modulo PZ and then raise it power any n, the automorphism of this is going to be GLN of Z modulo PZ. Okay. Again, if you are interested in counting what will be the cardinality of this, so this is basically you can think in terms of matrices. Okay. So, you have, so it is a 2 by 2 matrix. So, you have some A, B and C, D. So, this is the 2 by 2 matrix where entries are coming from Z modulo PZ. So, then if you think about the first row, so first row does not have any restriction other than the first row not being 0. Okay. So, the only condition that we have, this A, B should not be 0. So, that means, so the first row has exactly P square minus 1 choices. So, what is this P square minus 1? That is, you take Z modulo PZ cross Z modulo PZ and then you remove just 0 comma 0. So, you have these many number of choices for the first row because that is the only restriction. But if you think about what you need to fill in the second row, this is first row. So, this is the second row. So, the first row whatever you fill in the second row should be depending upon the first row. So, what the condition? The condition is the second row should not be multiple of the first row. Okay. This is one of the characterization of invertible matrices. Okay. If there are various characterization of invertible matrices. For example, one of the characterizations says if you take the rows and then think them as vectors in this 2-dimensional space, they must be linearly independent. So, the row 1, this is the row 1 and the row 2, so they must be linearly independent. So, that is the only condition. That means this CD whatever it is, it should not be multiple of this AB. Okay. So, that is the only condition where lambda comes from this Z modulo PZ. Okay. So, then how many choices you have removed? You have removed exactly P choices. So, total choices for CD is P square because it can come from any 2-dimensional vector, and then you just remove the line that lambda times AB, where lambda varies over Z modulo Pz. So then you get that many choices for C comma D. So the choices C comma D is exactly equal to P square minus P. So now what will be the total number of choices for AB and CD? Then if you think about it, it is exactly the product of those two choices because they are mutually disjoint. So the cardinality of GL2 Z modulo Pz is going to be exactly equal to P square minus 1 times P square minus P. Okay. So once you have understood this idea, it is not that hard to actually generalize this formula for GLN of Z modulo Pz. Okay. So that means when it comes to this particular type of P groups, okay, so where the P group is a group in which whenever you add any element P times, that becomes 0, okay, then it is easy to determine the automorphism group of that because one can view that P group as vector space over Z modulo Pz. Especially when it is finite, then we have very explicit formulas. So that is what this calculation actually tells us. Okay, I will actually stop here and then so maybe we will actually do some more examples of this computation of automorphism of group maybe in the next class. So so it's important to actually connect these various ideas that you see in group theory with the various other fields of mathematics, especially with the linear algebra and so on. So linear algebra, so they are again like somewhat easy abelian groups, that is what you are actually dealing with. So vector spaces are abelian groups, okay. So they possess much more structure than abelian groups. So they are also like linear, they have linear structure with respect to a field, okay. You have scalar multiplication and then you can add the vectors and then you can linearly extend any vectors and so on. Okay. Anyway, so I have already demonstrated some connection between this group theory and linear algebra. So we will again see some more examples like this in the future lectures. Thank you. I will stop here.